last time about the types of fundamental forces. Then we will come back to tension and normal reaction and those kind of mechanical forces. So coming back to the quick recap of the concept of the types of fundamental forces. There was gravitational force. Yeah, I started the recording, the impact recording. So just to give you a little more detail about gravitational force. The universal law of gravitation says that if you have two particles of mass m1 and m2, which are kept at a distance r, okay, we'll study more about this in the chapter of gravitation. Do this in more detail later. It's not really important right now in the Newton's laws chapter, but just from a general point of view of your understanding of the fundamental forces of physics, you'll see that there's this type of a force. There's always an attractive force, and the universal law of gravitation says that this attractive force is directly proportional to product of masses and inversely proportional to square of distance for particles, yes, of mass m1 and m2 and radii and so at a distance. Yeah, we are just revising that concept while others are joining. But I don't think I had discussed this formula in detail last time. At distance r, or even if we had discussed this formula, I'll just show another application of it. And the constant of proportionality is capital G, which is called the universal gravitational constant. Okay, now the sort of extension of this principle, yes, the value of capital D will, which is approximately 6.67 into 10 raised power minus 11 Newton into meter square divided by, Newton into meter square divided by kilogram square. Now, an extension of this concept is that, for example, if we have something like this, if we have a spherical body, like the Earth is typically a sphere, so we have a solid sphere of mass capital M, radius r, and you have a particle also of mass m, small m, let's say, and the center to center distance, suppose small r. So r is the distance from center of the sphere, C, let's say. So this point over here where the center of the sphere is C, and the particle, so the particle is the point mass P. Then also the gravitational attractive force that they experience because of each other's gravitational pull has the same formula. F is again equal to G capital M into small m divided by r square. Same formula, even though now it's not one particle, it's a solid sphere interacting with the smaller sphere. And also you can see that this is showing you the concept of the action reaction principle. the force acting on the particle due to the sphere is equal and opposite to the force on the sphere because of the particle. And we were talking earlier about this, the weight of a body on the Earth's surface versus, this is also an extension of the same concept. So for example, if you have this equation now, you have a solid sphere of mass m and radius r, and you have a particle is actually on the surface of the sphere. So then just the distance from center to this, it becomes equal to capital R. So you have the same formula of force, but only now capital R is replaced with small r. So here also the force becomes G capital M into small m, but divided by capital R square. Where capital R is the radius of the sphere. And again, you can see that this is an action-reaction pair. So this is what happens to a body on the surface of the Earth. So that is why on the surface of the Earth, what we write as F is actually the weight, and that mg is actually equal to G into mass of the Earth into mass of the body divided by r square. So acceleration due to gravity actually becomes this. This is what happens on Earth's surface. Yeah, it's told a bit. Okay. In this, ME is mass of the Earth, and RE is radius of Earth. So this is the nature of gravitational force. That the same formula that we have for two particles of mass m1 and m2, which are at a distance r, for force g m1 m2 by r square. This is the universal law of gravitation. This particular equation here is called the universal law of gravitation. Now, if you replace one of the particles with a solid sphere of mass capital M and radius r, okay, but the center of that sphere to the other particle, distance is r, then the formula of force is the same. But only that instead of the distance between the two particles, r now represents the center to particle distance. And in this formula or in this application, if it just so happens that the particle is not at a distance r, small r, larger than the radius, but it is right on the surface, so small r just becomes capital R, and the formula of force becomes like this. So this is indeed the gravitational force, for example, which is responsible for weight of an object on the Earth's surface. If you imagine the sphere with a giant sphere which is the Earth, then any particle or any body on the Earth's surface is experiencing the force we call weight, which is nothing but the gravitational pull of the Earth. So it's given by this formula, where capital R M will be nothing but mass of the Earth, written it as M, and capital R will be nothing but the radius of the Earth, which is given by R. So that also, for example, gives us the relationship between the value of small g and the mass of the Earth and the radius of the Earth. Okay. Anyhow, so don't worry about this. I mean, you don't need to know this too much in detail right now. There will be a chapter called Universal Law of Gravitation. They will study about this in more detail. So this first part is the comparison between a situation where you have two particles, M1 and M2, which are at a distance r, versus one solid sphere and a particle, which is at a distance small r. And the third example I've shown you here is when that particle actually happens to be on the surface of the sphere. But every time you can see it's the application of the same formula or the same universal law of gravitation. Now, this universal law of gravitation is not derived from anything else. It is actually coming from the fundamental nature of gravitation. It's an experimental law, which is derived from the fundamental nature of mass, how mass interacts with other mass. So that's why we call this one of the fundamental type of forces in physics. One of the four types of fundamental forces, which is the gravitational force. Right. So, as I said, for this chapter right now, you don't need this formula. This just I'm giving you for your general knowledge. We'll be discussing more in detail about this in a later chapter called gravitation. So this you can just read from the notes later when you go through it. Now, similarly, the second type of fundamental force we were discussing, yes, is electromagnetic forces. The second type of force was electromagnetic force. So in this, for example, electrostatic force, that is the interactive force between static charges or charges at rest, and they are given by a fundamental law called Coulomb's law, which we will start study as part of our class 12 syllabus. This will be in class 12. But I can just tell you the basic idea about it. So according to Coulomb's law, if we have, for example, two positively charged particles, which are at a distance r, and they are q1 and q2, then they experience very similar kind of expression to gravitational force, but they experience repulsive force. They experience repulsion force, where again that force is proportional to product of charges and inversely proportional to square of distance. Or in fact, that force is a constant into product of charges divided by r square, where that constant of proportionality is approximately this 9 into 10 raised by 9 Newton meter square per Coulomb square. C over here stands for Coulomb, which is the SI unit of charge. For example, you know that one electronic charge is 1.6 into 10 raised by minus 19 coulombs. So the charge of a proton is positive of this electronic charge. The charge of a neutron is 0, and the charge of an electron is negative of the electronic charge. So here the force will be in newtons when you express q1 and q2 in coulombs and the distance r in meters. So this particular principle is called Coulomb's law. And similarly, Coulomb's law also tells us that if we have opposite charges, so we have a charge positive, but the second charge is suppose negative, q2 is a negative charge, and they are kept at a distance r, then it will be the same formula of force, but there will be attractive force. So here there will be attraction force given by the same formula, same magnitude. Yeah, this is in 12th. We'll be studying about this in detail in 12th. So this is about what we call electrostatic force, or the force between static charges. The static charges का मतलब क्या है? Charges at rest. Now similarly, so as I said, you don't need to write down this in detail right now. This is just to give you some idea about these forces. Similarly, yeah, I'll talk a little bit about strong and weak forces also. Similarly, we have magnetism or magnetic forces. So they are force between moving charges or currents. So it turns out, for example, that if we have suppose a current carrying wire, if this is suppose a conductor, a conducting wire, which is carrying current in this sort of direction, it's carrying electric current in this sort of direction. So what will happen is at all these points, it will create magnetic field. For example, at a point below over here, it will create magnetic field which is going into the plane. We show magnetic field going into the plane with a cross to show a vector sign which is going away from you. So this creates magnetic field. We represent by the vector V, which is into the plane. Whereas at points like this, it creates magnetic field coming out of the plane. Where it creates magnetic field coming out of the plane. So now if I have another charged particle here, so this is a current I. The current I is nothing but a stream of moving charges. It's nothing but a stream of moving charges. This is actually electrons moving in the opposite direction. No, they're not neutral points, Krishna. The crosses represent the vectors going into the plane. Okay, so the cross sign stands for a vector into the plane. And similarly, the dot on that side represents a vector coming out of the plane. And you see the tip of the arrow, the head of the arrow from top. So magnetic field B into the plane of the screen. Into means going away from you. That vector sign going away. Now it turns out that if you have a charged particle here, let's say like this, which is moving with a velocity v like this. Okay. So that charged particle experiences magnetic force. The moving charge will experience magnetic force given by the formula Q into V cross V. So in this diagram, you can see the direction of V cross V for this particle here will be in this sort of direction. Because V is pointing like this and B is into the plane. So, sorry, it will be opposite. It will be. So point your thumb along V and your fingers going into the plane. So you can see that V cross V will point like this. So it will experience a sort of attractive force towards the current. Neutral points are slightly different, but I think when we come to magnetism, I'll explain to you in detail what they are. So this kind of force, this expression, is called the Lorenz Force. Just like that one was called the Coulombic force. So this is another part of, yeah, all this is, but the Maxwell's theory, Piyush, is like, you know, it's a broader thing, but yeah, these are elements of Maxwell's theory of electromagnetism. Maxwell's theory of electromagnetism, it has more to do with how changing electric field generates magnetic field and changing magnetic field generates electric field. So it is more about what we call electromagnetic induction. This is just about electromagnetic forces actually. So that's the part actually that comes before Maxwell's equations. Okay, but yeah, I mean you can say Maxwell's theory is inclusive of all these ideas of electromagnetism. So cumulatively, electrostatic and magnetic forces together are called electromagnetic forces. So electrostatic and magnetic forces, okay, they are nothing but the interaction between charged particles or bodies, and they are collectively called electromagnetic forces. Only magnetic is when they are in motion, and electrostatic is when they are static or at rest. But cumulatively is the effect of charge, and that's why they are called electromagnetic forces. And that is the second of the four fundamental types of forces. Now, as we were discussing last time, that in all of the forces that we experience in most of the macroscopic world around us, which includes what you see of physical experiments as well as what we use in technology and engineering, typically everything is a combination of gravitational and electrostatic forces. So in everyday life or in our experience of the physical universe, okay, all the forces we experience, for example, in a solar system, okay, or in the case of a satellite orbiting Earth, okay, or in the case of path of a comet, these are all part of which type of interactions? Gravitational. Okay, weight of a body, okay, on Earth, or weight of a body on the moon surface. You go to the moon surface, what is the weight you will experience? These are all coming as under the interaction, the gravitational kind of interaction. Yeah, sure, yes. Okay. You can rejoin. Whereas, for example, mechanical forces, for example, normal reaction, okay, friction, yes, very good. Okay. So collectively, these are contact forces, okay, or tension or reaction force. Okay. These all come under the category of what? They come under the category of electromagnetic interaction. Okay. Or yeah, there's gravity on the moon also. Okay. Or for example, in electrical circuits, okay, whether you are having, something to do with power systems like high voltage electric lines, okay, or you are talking about microelectronics, that is circuits with semiconductor devices, okay, ICs, microchips, whatever be the case. But इसमें जो भी interaction हो रहा है, they are all basically what? They are again electromagnetic interactions. Okay. You're talking about something happening in a electrolytic cell, okay, or you're talking about something happening in a photovoltaic cell, okay, or you're talking about something happening in a hydroelectric turbine generator, जो भी है, ये सब they are part of electromagnetic interactions. So most of the things that we experience in our everyday lives, they come under the category of either gravitational, if we are talking about things to do with celestial bodies and astrophysical elements, or they come in the category of electromagnetic if we are talking about mechanical forces like this, or if we talk about the types of forces which are in electrical appliances, electrical circuits, electrical devices, etc. They all come under the category of electromagnetic interactions. Yeah, magnetic force, Sarvesh, in short, is the force between moving charges. So magnetic forces in our everyday life we experience in two situations: when we have current carrying conductors near each other, or you have a charge particle projected near a current carrying wire, it will experience magnetic force. Or we also experience magnetic forces in naturally occurring magnets. Now, in naturally occurring magnets, we don't see any current flowing or we don't see any charge moving. So how come there is magnetism? So the reason there is magnetism is because in a naturally occurring magnetic material, which is called ferromagnetic materials, is the electronic orbital motion of the electrons that cause magnetism. So the individual electrons that are moving in the electron clouds, etc., they are actually by their own motion, and those electronic cloud motions or those electronic orbital motions, they are all linked together in such a way that they create the same kind of effect that an electrical current in a coil or in a solenoid or something like that creates, and that's why they create magnetic field. There is gravity on moon, beta. On moon there is gravity. Okay, that is why a person standing on the moon doesn't need to be tethered to a spaceship or something. He experiences much less weight compared to Earth because the mass of the moon is a lot less. But there is some gravity on the moon surface. Okay, in fact, you can see videos on YouTube and all of people doing walks on the moon and all that. And yeah, there's 1/6 roughly of the gravity. So, a typical person trying to walk around the moon will be very awkward. They'll be kind of jumping around in huge steps. Okay, as if his feet are loaded with some giant springs. So uchalta hua, like a mechanical robot, he'll be jumping. Because if you see photos of Neil Armstrong and all, video footage, you'll understand that. Okay. Then there are a lot of interesting things actually. It's one of the reasons why something like the moon does not have an atmosphere, whereas Earth has an atmosphere, because the gravitational field on the moon's surface is not enough to keep the gas molecules in an orbital motion around or in a confined atmosphere around the moon. Whereas the Earth's gravitational field is strong enough to create a gravitational pull on the atmospheric air molecules that they don't escape to space. They remain around the Earth. That's another interesting factor actually. There's a very interesting relationship between the gravitational field of a planet and the temperature of the surface. Okay, and that relationship tells whether the temperature and the gravitational field have a proper suitable kind of relationship between each other to sustain an atmosphere around it, or will gaseous molecules tend to escape away to space. Yeah. Yeah, Jupiter, yes, Smith is a little, it's a difficult case to visualize in that sense anyway, because Jupiter is a giant gaseous planet actually compared to. But yeah, definitely in Mars, for example, the gravitational field will be more than compared to Earth. That's what they've predicted and all. Okay. Now coming back to our discussion from earlier, the third and fourth type of fundamental forces we'll just discuss in detail. Yeah, Samat, Venus has different properties. Actually, the relationship has not only to do with mass, it also has to do with radius. Like you saw in the formula I had written earlier, that G was capital Gm upon R squared. So it depends on the relationship between the mass of the planet and also the radius of the planet. So coming back to fundamental forces. So the third type is called the strong forces. Okay. Or they are called nuclear forces. Okay. So these have a very interesting property. These nuclear forces are what is called short range forces. Not very much is known about them, like electrostatics, magnetism and gravitation. So we don't have any exact formula for them, but we know one thing, that nuclear particles, or what we call subatomic particles, in the nucleus experience very strong attractive forces when the distance between them is very short. So this short distance should be of the order of angstroms. that is the nuclear radius. Sorry, of the order of Fermi, by mistake, not Armstrong's. Atomic radius is Armstrong. Fermi. 1 Fermi is 10 raised to minus 15 meters. Yes, nuclear forces are strong forces. Another name for strong force is nuclear forces. Okay, whereas when at larger distances, for example, are of the order of Armstrong, where Armstrong is 10 raised to minus 10 meters, the nuclear force tends to zero. It tends to become zero. So that's why they are called short range forces, because they operate in very short range. Okay. So basically, these forces are the attractive forces between proton-proton or proton-neutron or neutron-neutron. These type of particles, but when they are packed together in that smaller space, which is the size of the nucleus rather than the size of the atom, then they experience these strong forces. And this is responsible, yes, it has to do with radioactivity. So these nuclear or strong forces are responsible for something called binding energy of a nucleus. Okay. And that's why extreme nuclear radiation energy is emitted in any nuclear reaction. So, for example, radioactivity. In radioactive decay, there is extreme amount of radiation energy which is responsible. In the case of chain reactions, in atomic bombs, there is chain reactions of nuclear level, okay, or in atomic energy generation. A small amount of mass can give extreme amount of energy. Yojit, to answer your question about gravity and orbital motion, it is more to do with the relationship between the radius of the orbit and the time period, has to do with the gravitational pull. So when you see that around a heavy mass, a smaller particle or a smaller mass is in orbital motion, the time period of orbit, that actually depends on all these things. It depends on product of masses and inversely proportional to the radius. So we will see that in another chapter, because what happens is in the orbital motion, the centripetal force, the so-called centripetal force, mv square by r, that is coming from the gravitational attraction. So that is where you see that the relationship, v becomes proportional to m into m upon r. So time period is inversely proportional to v and all that. So from that it comes. Yes, Samaj. So that is the reason why nuclear energy production is a process in which very small amount of mass consumed of nuclear fuel generates a very high amount of energy. In megawatts or like that, in gigawatts, very small amount of nuclear fuel consumed will liberate a very, very high amount of energy, because the energy that is getting liberated, the forces which are responsible for that energy is not electrostatic or gravitational force, but it is rather the nuclear forces. So they are many orders of magnitude higher compared to the electromagnetic or nuclear forces. Whereas something like an AC dynamo or a wind turbine generated power supply or electrolytic cell, etc. These are all harnessing energy which is as a result of electromagnetic interaction. Whereas a nuclear power plant is harnessing energy which is liberated as a result of nuclear changes or nuclear forces of interaction. So it's many orders of magnitude more. So in our everyday life, we don't really experience it, but yeah, in everyday examples, a nuclear power plant or an atomic bomb or radioactivity, these are physical systems where the nuclear forces or the strong forces inside the nucleus are basically responsible for the system. What we do to utilize the nuclear energy is that this energy liberated is converted to electricity. No? It is converted to electricity again using a turbine. But the source of the energy in the first place is what? It's a nuclear change. It's a nuclear reaction. Arjit, I just explain the question to me better once more. Which diagram is that? No, Ligit, I've not made any particular diagram. I'm just giving you some examples of strong forces. Yes, surveys, that's correct. It's a right side in the end. Yeah, I'll just leave you with the note for a minute. Achha, that diagram, sorry. This was a different question. This is not related to nuclear. Okay. Somebody in between had asked me a question related to orbital motion. So I was explaining circular orbit of a planet around a star or something like that. Yeah, nuclear energy in that sense, I mean, for example, solar energy. Another example of this is solar energy liberated by the sun. That is coming from nuclear reactions in the sun's core. So they liberate huge amounts of energy. And it never ends. But it will end someday. But that in our scale is a huge amount of time. But in the time frame of the universe, any star also has a lifetime. But that lifetime will be billions of years. So in the human, in the human species scale of things, it's like infinite time. So everything is about order of magnitude. No, not necessarily. The nuclei are very small, but radioactivity is displayed, surveyed by both heavy nuclei as well as light nuclei. So, extremely light nuclei like helium, beryllium, etc. also undergo radioactivity. But when they are fused together, and those type of reactions are called fusion reactions. Whereas extremely heavy nuclei like uranium, thorium, etc., they break into smaller nuclei, and those are called fission reactions. Radius of the nucleus is strong than nuclear forces, no better. The idea is, see, nuclear force operates within the nuclear size, because nuclear force has that nature that it's a short range force. So it only operates where the distance between the subnuclear particles is extremely small. So that's what happens inside a nucleus. The nature of the nucleus is such that within a very small volume, a spherical volume whose radius is of the order of Fermis, the subnuclear particles or the subatomic particles are packed together. Okay. Whereas if the same set of protons and neutrons that constitute of the nucleus are allowed to occupy a larger volume, like the volume of the whole atom instead of the nucleus, there would be hardly any nuclear energy. because there would hardly be any interactive force between them. Okay, so the nuclear force is extremely large. That's what keeps the nucleus held together. Otherwise, the nucleus would disintegrate, no? Because protons would repel each other and they would all go to infinity. Okay. And finally, the fourth and final type of fundamental force is called the weak forces, or sometimes also called electroweak forces. So these are the interactions between the fundamental particles of physics that are the building blocks of all matter. For example, protons and neutrons are made up of something called quarks. Then we have electrons, positrons, which is the antiparticle of electrons. Then you have neutrinos, and many such, fermions and bosons, etc. So this entire domain comes under the category of particle physics. So it's a research area. So it's way beyond the scope of our study over here. So that's why we don't get into electroweak forces. Yes, there is the concept of down and up protons, quarks. Okay, quarks have something called spin, and that's where you would have heard the term down quarks and up quarks. Okay. So the nature of charge also comes from the nature of the quarks or the combination of quarks, etc. So anyway, all this is like extremely high-end physics. It's a part of research in particle physics. So we won't be getting into that. Yeah, God particle, which is also called the Higgs boson particle. Also called, also known as God particle. No, there is no oh my God yet. Okay. There might be. So anyway, so these two things are not both nuclear forces and weak forces is not something that we're going to study in our 10+2 syllabus. Okay. Nuclear forces, still to a certain extent we can talk about because we will know about radioactivity and things like that. Neutrinos are very tiny particles which are extremely light particles, okay, emitted during beta decay reactions. During beta decay radioactive reactions. God particle was discovered in CERN. So these are some things that you can read about on internet in terms of general knowledge. But okay, beta decay, beta alpha beta radiation, that decay, when proton converts into neutron and electron, rather neutron converts to proton and electron, it's called a beta decay. That one. Okay, so this is about the fundamental forces. Now coming back to our mechanics part, Okay, so we were discussing about normal reaction and tension last time, so we will continue with that now. Okay. So coming back to Newton's laws applications. So we were seeing common mechanical forces. So we'll talk a little bit more about these today. So normal reaction. We saw that it is defined as the contact force in the direction. So the proper definition of normal reaction is it is a contact forces in the direction perpendicular. Okay. Or perpendicular is also called normal in geometry. Okay. To the plane of contact. Between two surfaces. Okay, so this is the proper definition of normal reaction. It is a contact force, or their contact forces in the direction perpendicular, or another word for it is in the direction normal to the plane of contact between two surfaces. So through examples we will understand more about this. Okay, so the first and most fundamental example. So written on the definition, people. Yeah, so it is as a result of course, fundamentally we have understood it is electromagnetic forces at the molecular level, molecular or atomic level. Right, so the most common example of normal reaction right, so finished with this. Common example is when the weight of a body, okay, or bodies for that matter, plural, presses it or presses them against a horizontal surface. So then it creates vertical normal reaction. So for instance, we already seen this kind of example many times. But just for the sake of understanding in detail, so this is a block of mass m, and this is some kind of a horizontal surface. So what happens is that as far as the block is concerned, the earth is pulling it down because of its mass. So the earth is pulling it with the weight. This is the weight or gravitational pull due to the earth. So what this does is that this pushes it against the surface. So the surface reacts by applying an upward force like this, which is actually a distributed force. Okay, so there are these tiny force vectors which create a net force in the upward direction, which is what we call the normal reaction. Okay, so N over here becomes a net upward contact force applied by the surface on the block. So that normal reaction is actually more like a pressure into area. What is happening is the block lying on this surface is applying force due to pressure like this. This is on the surface. So the surface applies equal and opposite force like this on the block. So the lower surface of the block, this face of the block, which is against the horizontal floor or whatever, it's experiencing upward force vectors because of pressure. So ये पूरा cumulative force को हम क्या बोलते हैं? हम normal reaction बोलते हैं. You understood now? So in this case, what will happen? The normal reaction will be now because the block is in equilibrium. Okay. So that means the net force on it should be 0. Okay. So that means the normal reaction is exactly equal to mg. Okay. That means the magnitude of normal reaction n equals the weight. They are not equal forces, because one force is pointing upwards and the other force is pointing downwards. But they are equal in magnitude because what happens is normal reaction is what we call a self-adjusting force. It adjusts itself according to whatever it is reacting against. So क्या हो रहा है? Weight of the block is pushing it down against the surface. So according to whatever the value of the weight, the surface has to react by applying an equal and opposite force, which is the normal reaction. Okay. If the surface is not able to react that way, then the object will not remain in equilibrium. So for example, if you place that block on the surface of water, it's a metallic block or something. Now the water surface cannot apply a normal reaction, which is enough to balance the weight. So it will not be able to adjust itself to balance the weight, and instead what will happen? The object will sink. But if you keep it on a rigid surface like a wooden table, or a metallic surface or a stone surface or something, what will happen? The stone surface or the metallic surface or whatever, it will be able to adjust the repulsion force it's applying or the normal reaction force it is applying. Okay, and balancing it. No, the chapter is mostly about numerical problem solving, but we have to understand the theory part first. Na? Yes. So is it clear this example of normal reaction? This is the most common everyday example of normal reaction. So just make a note of this first. That is a different reason. So certain objects can be made of materials which have less density compared to water. So then water applies something called a buoyant force. Now, buoyant force is because of a different reason. It is because of the pressure under water, which increases with depth. Okay, so just make a note of these points and you'll understand what normal reaction is. Okay, now see, I was telling you one thing, one important point here, that normal reaction is self-adjusting. So let's understand this point with another example. It's a self-adjusting type of force. That means it adjusts itself according to external situation. So what we mean by this, let's understand with this example. So what is happening is, I have a block of mass 50 kg, and let's take G as 10 meters per second square, lying on a horizontal surface. So we all know that in this case, what is the normal reaction going to be? It's going to be equal to 500 newtons. So यहाँ पे on the block, what is the normal reaction acting going to be? So we know that on the block, the weight is going to be balanced by the normal reaction. So the normal reaction is going to be mg. So it's going to be equal to 500 newtons in magnitude. Okay, this is very simple thing. We just saw this above. However, now let us do one thing. On the same thing, if I make a change, and what I do is, while this block is on the ground, while this block of mass 50 kg is on the ground, I am applying an external force on this block, pushing it down. So there's some external agent who's pushing this with a force like this. So this is now, so let's say this is a force of 100 newtons. So now an external agent is pushing downwards on the block with F external as shown. Okay. So what is the normal reaction in this case? Normal reaction नहीं होता तो गिर जाता बेटा. Like if you just leave a block suspended in air, not against the surface, what will happen? Only mg will be acting on it, so it will accelerate downwards. So its acceleration will become g. It will be in free fall. You understood, na beta? So what is preventing the object from falling down in free fall? It is nothing but the normal reaction. So what we'll observe, yes, 600 Newton is the correct answer. So what we'll observe here is that the block remains at rest, no? But this time on the block there is weight mg of 500 Newton acting. There is this downward external force of 100 Newtons. Okay. So why it is not falling ultimately? We are observing it's lying stationary on the surface because the normal reaction is adjusting itself. It's increasing immediately. जैसे मैंने 100 न्यूटन का फोर्स लगाया, normal reaction बढ़ के कितना हो गया? 600 न्यूटन हो गया. I didn't have to tell कि okay, Baba, now normal reaction increase. On its own, it will immediately increase. So we'll see the acceleration of the block is 0. What we observe is that the block is stationary on the surface. Okay. So it's in equilibrium. So why it is in equilibrium in spite of applying the external force? Because normal reaction adjusts the excess amount of force. So normal reaction now balances mg plus F external. You can see normal reaction automatically adjusts. Okay. So from that example, the normal reaction adjusts on application of external force. So that's one example of understanding how normal reaction is a self-adjusting force. It automatically adjusts according to the external situation. Okay, so is this situation clear? The block was lying on the ground initially with no other external force. So normal reaction was equal to 500 Newton. But जैसे ही मैंने यहाँ से इसमें ये change लाया, that the external force started acting on it, वैसे ही the normal reaction would suddenly change from 500 to 600 Newtons. Weight, on the other hand, is not something that self-adjusts. Weight remains 500 Newtons, irrespective of whether I'm applying any other external force or not. Yeah, it depends on the shear strength and all that, but here, we are assuming that the surface is rigid. Suppose the surface is made of cardboard. Now in 600 Newtons, it might be able to support, but I increase the external force to 150 Newtons from 100. And I might say that, okay, the surface is not able to apply 650 Newtons, instead it breaks. The cardboard tears, or there's a crack that appears in it and it goes straight down. Okay, but that's a different matter. Okay, so understood this example, people? What I meant by saying that it is self-adjusting in nature. Now let's see another example. Now this time what is happening is, it's again pretty much the same situation. Just can't get these aligned properly. Okay. Now this time additionally I'm specifying that this is what we call a smooth surface. So friction is not there, it's frictionless. Okay. And this time let's say this mass is 10 kg and take g equal to 10 meters per second square. Now again I'm going to make two situations, so let me just set that up first. Now in case 1, what is happening is I'm applying an external force like this. And in case 2, I'm applying that same external force like this. Or you can even say that I'm applying it from this side. I'm pulling it from this side. So दोनों केस में ये फोर्स ऐसा है, so in both case 1 and case 2, external force of magnitude, let us say 20 newtons, is applied at theta equal to 37 degrees with respect to horizontal. Okay, in each of these cases. So you have to find out the normal reaction and the acceleration of the block in each case. So find the acceleration and the normal reaction on the block in each case. So just try this out quickly and tell me the answer. Dhruv, not correct. 6 तो हो नहीं सकता ना बेटा, because the mass is 10 kg. So to create a horizontal acceleration of 6 meters per second square, you need a force of 60 newtons. यहाँ पे तो Fe 20 न्यूटन है, तो उसका हॉरिजॉन्टल कंपोनेंट कैसे हो सकता है इतना, है ना? Yes, that is correct. Piyush, your answer is correct. Aditya, your answer is correct. So you can see that it's all about vector algebra. In case 1, ये जो हम फोर्स लगा रहे हैं, this force, it is the same thing as a combination of horizontal and vertical component. This force F, you can treat it as a combination of, so if this angle is theta, it's a combination of a horizontal component of that force Fx and a vertically downward component of that force Fy. And Fx will become F cos theta, so that will become 20 into 4 by 5. Cos 37 is so 16 Newton, and Fy will become F sin theta, so 20 into 3 by 5, so 12 Newton. Okay. So this is the same thing as saying that, okay, on the block, I'm applying one force horizontally like this and another force vertically downward like this. I'm pushing this down with a vertical component of 12 Newton, and I'm pushing it horizontally with a horizontal component of 16 Newton. Okay. And apart from that, of course, there is the earth which is pulling the body down with a gravitational force of 10 kg, na? So 100 Newton, okay. And some kind of normal reaction that the earth will be applying, sorry, the surface below will be applying, which will be in the upward direction. You want to calculate, okay. And this is having some horizontal acceleration. So along the horizontal axis, which is our x-axis, what is happening is that the net force is Fx. That should be equal to mass into acceleration. Net force is equal to mass into acceleration. So 16 newtons is equal to 10 e. So our horizontal acceleration is 1.6 meters per second. Theta is given in the question 37. What is the what is this is given. That's part of the question. Obviously, without that given in the question, we can't find it. And in the vertical direction, or along the vertical axis, or the y-axis, Fy plus mg has to be balanced by normal reaction, because the net force has to be 0. there is no vertical acceleration. There is no vertical acceleration. So normal reaction is becoming how much? It is becoming F5, which was 12 newtons plus weight, which was 100 newtons. So the normal reaction is becoming 112 newtons. Okay. So you have to be careful about components. Some of you have taken the horizontal component 12 and the vertical component 16, but remember the proper algebra here. Like this. Whatever angle this is making, this component will be the cos component, and this angle is 90 minus theta. So this component will be how much? It will be f sine theta. So this is resolving f into components. Yeah, Kevin, your second part is also correct. Now, those who have finished the first part, writing it down, try out the second part yourself now. Okay, so in the second part of the question, you are applying a pulling force from this side. So that again its angle with the horizontal is 37. In both case 1 and 2, the external force of 20 newtons is applied at 37 degrees with respect to horizontal. Acceleration will be same, that's correct. But what about normal reaction? Yes, Devansh, your answer is correct. Austin, it is correct. Good. Aditya, एक बार calculation check करो, but the idea is correct. You made a subtraction mistake, but okay. So just like we've done the solution of question 1, but now only thing is कि इसका जो vertical component है, that is in which direction? It's in the upward direction. It will not be in the downward direction. Yeah, Aditya, answer is correct now. Yes, Smith, correct. Ranak, correct. Good. Yes, exactly, Samar. Yeah, Sarvesh, the idea is correct. Now let's do the calculation. Okay. So I'm just working it out here now. So in the second case, the actual forces acting on the body are the external force F, which is acting like this. Okay. Of course, weight, which is acting downwards, and normal reaction with which the floor is pushing body. degrees. Normal reaction mg and this external force, which is again at theta equal to 37 degrees. So this is 20 newtons, 10 kg mass. So now break this into components. So when you break this into components, you have horizontal component of F, but this time the vertical component is like this. So ये force का vertical component कितना हो जाएगा? It will be F sin theta or 20 into 4 by 5. So it's again the same, but it's opposite in direction compared to the last one. Whereas the horizontal component of force is F cos theta. So again that will become 16. So these are the components. And rest of the things are same. mg is 100 newtons, and this normal reaction upward we want to calculate how much it is, but it's accelerating horizontally. So along the x-axis, what is happening? The x component is providing the linear acceleration of m. Okay, so again 16 is equal to 10 e. So e is equal to 1.6 meters per second square. But along with that, along the y component, what is happening? This time Fy plus normal reaction together are balancing mg, because acceleration is 0 along the y-axis or along the vertical. This is what is happening. So this time our normal reaction will become mg minus the vertical component. That will become 88 newtons. So understood once again how normal reaction is self-adjusting according to how we are applying the force. Yeah, sin 37 is 3 by 5. That's why that component was 12. Oh, sorry. Yeah, correct. Just make a correction here, but the value is correct. It's 12. And this is 4 by 5. Correct, Sudha. Right, so hope both the parts of this example are clear. Now let's see another example. Now this time my block is lying against the corner of a vertical wall and a horizontal floor. Okay, so this is wall, this is the floor, and the mass of this is 50 kg. And what I'm doing is I'm applying force of 200 newtons at theta equal to 30 degrees with respect to horizontal. So find normal reaction on the block due to the floor. How much normal reaction the floor is applying, and normal reaction by the wall. It's in surface with, it's in contact with two surfaces. Yes, very good. That's correct. Viraj, that's correct. Dhruv, that's correct. No, Samarth, in the previous part it was the other way. N plus F5 was mg. Just a moment. Going back to this. देखो इस diagram में क्या हो रहा है? The vertical force is acting in this direction. Okay. Normal reaction is also acting in the same direction, and mg is acting in the opposite direction. What the point now? Mg is acting downwards. Okay. So that is why this equation became this one. That the two vertical forces together are balancing the downward force. Is it clear, Samarth? In the first part, it was the other way. First part, it was like this. First part, F5 plus mg was equal to n. F5 plus mg was equal to n. Second part, it was the other way around. F5 plus normal reaction was balancing the weight. And now come to this question. Yeah, Dhruv, your answer is correct. So again, the main thing is resolving the forces and then balancing the net force. So to resolve this force, you need to understand that this force has a magnitude of 200 newtons. And it is such that this angle is 30 degrees. So that is why my horizontal component will become cos 30 and the vertical component, which will be in the vertically downward direction, will be sin 30. Okay. So this y component will be f sin theta over here, so it will become 100, and the x component will be f cos theta, which will be 100 root. So this is the main thing. Once you understand this step, the rest of it is easy. So once you understand this, now just see all the forces acting on the body. So as far as all the external forces acting are concerned, mg downward is 500 newtons. Then this x component of force, this one was 100 root 3, and the downward component of force was 100. Now the floor is pushing back with some normal reaction n1, let's say this is by the floor, and the wall is pushing back with a normal reaction, let's say n2 is applied by the wall. Now acceleration of the block should be 0. Okay. So both horizontal and vertical forces should balance. So horizontal and vertical, all forces should balance. So Fx should be balanced by n2. So the normal reaction that the wall is applying will become 100 root 3 newtons. And Fy plus mg should be balanced by n1. So n1 will become 600 newtons by the floor. Okay, so hope this one is clear to all of you. Okay, now let's look at the next example. Now this is where things start getting a little bit more tricky, because we bring inclined planes into this situation. So this is a smooth inclined plane. This is smooth wall. This angle is my favorite angle, 37 degrees. Now what is happening is we have like a spherical ball which is rested like this. This is a solid sphere of mass 5 kg and take g as 10 meters per second square. So find the normal reactions on the sphere applied by the inclined plane and the wall. How much normal reaction the inclined plane is applying on the ball or the solid sphere, and how much normal reaction the vertical wall is applying there. Then it's at rest. It's sort of lodged between, it's sort of stuck between the wall and the inclined plane. Okay, so just give this some thought and try it out. So the major thing is going to be here the application of vectors. Remember that normal reaction will always act perpendicular to the surface. So the inclined surface will apply a normal reaction in a sort of diagonal direction. So that normal reaction will be in a direction making 37 with a vertical, whereas the wall will make a horizontal one acting on it. Okay. Yeah, I'll tell you the values. Okay. Remember the weight of it is 50 newtons. No, unfortunately the values are not correct. यहाँ पे normal reaction due to the floor, or I mean due to the inclined plane, will not be mg cos theta. When I make the diagram, it will be clear to you why that's the case. If it was sliding down the incline, then what you're saying is correct. But here it's rested against the wall now. So the wall is also pushing it with a horizontal force. So to be extra careful. think I'll finish it around. Take another 20 minutes. Okay, so let's see. Yeah, Sujal, I think your answer appears to be okay. Achha, so first of all, let us see the mechanical situation of this. Okay, so again, in the interest of saving a bit of time, let me see if I can recycle the diagram a little bit. Just a minute. I'll reshare the. Okay, now the forces here are very interesting. That's the main thing you have to understand. So see, this surface, the one which is the inclined surface, this will be applying a normal reaction in this sort of direction. ऐसा normal reaction applying. This sort of direction. Okay. So that direction has to be such that it's along this normal line, perpendicular to this surface. So this normal reaction is N1, that is passing through the center. And whereas, because this is a vertical surface, this will apply a horizontal normal reaction at the contact point. Let us say this is N2, and this also passes through the center. Whereas the weight of the object, that is vertically downwards. So these are the three forces which are acting. Okay. So are you clear with this diagram, all of you? Teeny forces हैं because they are smooth surfaces. So the total number of forces acting in the system or on the body are these three. Okay. Now, as far as understanding the directions are concerned, I mean understanding the angles are concerned in a little bit more detail if you want to understand. So देखो ये जो normal reaction act कर रहा है, that is along this line. That's along a line like this. With this angle is 90 degrees. It's along this line. So we have to be very careful when we understand the angles involved with it. So we go. Last time also I told you once a rule of thumb. If the inclined surface is making an angle theta with the horizontal, ये angle अगर theta है, so यहाँ से you drop a perpendicular downwards like this. So this angle will be theta. Okay. So this normal reaction is acting at an angle which is theta to the vertical. Understand? This normal reaction is acting at an angle which is theta to the vertical. Okay. So therefore, this normal reaction will have a horizontal component this normal reaction N1 is like this now, that this angle is theta equal to 37 degrees. This angle. Okay. So ये angle theta है. So that means इसका ये वाला component कितना हो जाएगा? This component will be N1 cos theta और 4/5 N1 और उसका ये वाला component कितना हो जाएगा? N1 sin theta और 3/5 N1. So pay very close attention to this diagram to understand the resolution of this. So whenever we have an inclined surface like this, any object that is kept here, उस पे जो normal reaction act करता है, that is along this line, So that is always such that if this angle is theta, then here this angle will be theta. This angle will be theta. Just remember this like a simple rule of thumb. So the inclined surface is at theta to the horizontal. Okay. So that always implies that the normal reaction will be at theta to the vertical. The more you get used to this, the easier it will become for you to directly do these type of questions without making so many diagrams and all like I'm making right now. Okay. So now let's come down to balancing the forces. So coming back in that diagram, now if you see the forces, what all forces are acting? There is this force that was acting along this line. We divided it into two components. We saw that this component was 3/5 N1 and this upward component was 4/5 N1. This force has been divided into these components. Then what else was acting? The wall which was on the left, it was applying a normal reaction N2, which is like this towards the right. And the gravitational pull of the earth was pulling it down at mg. And the acceleration of the body is 0. So now taking this as, so along the horizontal, what is happening? N2 is balanced by 3/5 N1. So that is my equation 1, let's say. And along the vertical, what is happening is that mg is balanced by 4/5 N1. That's my second equation. Okay. And now solving the two equations, I will get the values of N1 and N2. Okay. So I'm coming to the solution, but first, just make sure that you understand this in detail. Okay. Take your time and make sure you understand this diagram first of all. Then the details about the force N1, direction of N1, and resolution into components. For N1, that part is 0. And then finally, the net force should be 0. And this is the application of Newton's second law. We don't know. यहाँ पे हमने Newton's second law use किया because the acceleration is 0, so net force should be 0. Okay, so hope this is clear to all of you, this question. I mean, up to this point. Yeah, so now just solve. So from here, from the second equation, you can see 4 by 5 N1 is equal to the weight which was 50 newtons. Okay. So that means N1 is how much now? 62.5. Okay. Or N1 is 5 by 4 times. So that will be this. Okay. And then N2, and then from equation 1, N2 is 3 by 5 times N1. So that is so 37.5 newtons. That is becoming your N2, and this is becoming your N1. So these are the normal reactions. Yeah, so the second assignment which I have said today will have more detailed questions about contact forces, normal reactions like this. Okay. But wait, just want to discuss a couple of more things with you. Three-dimensional diagram की जरूरत ही नहीं है ना बेटा, because all the forces are in the vertical plane. So we don't need any three-dimensional diagram. अच्छा, the third diagram. So see, ये जो forces है ना, उनको ही मैंने यहाँ पे दिखाया. Okay. But N1 is resolved. So in this diagram, N1 has been resolved into components. Which one? This one? This diagram? This diagram? So this is just giving you the general rule of thumb कि कोई भी inclined surface है, उस पे कोई सा भी body है, it can be a circular body, straight body, whatever. The direction of normal reaction is like this. It's always perpendicular to this. This is applying normal reaction like this. So therefore, if this angle is theta, the angle that this is making with the horizontal, so therefore this angle becomes theta. Okay. So this general principle is shown. If the incline is at theta to the horizontal, then the normal reaction applied by that incline will be at theta with the vertical. Perpendicular to his plane. So this, to summarize this, what we've done over here, we use a particular method for solving Newton's second law. So when applying Newton's second law, that is net force is equal to mass into acceleration to a body on which multiple forces are acting. Aditya, there's no need for so much confusion. Okay, let's go back to that point. Inclined surface ऐसा है, and your horizontal is like this. So if this angle is theta, now whatever kind of object is lying over here, whatever the shape of that object, it doesn't matter. Inclined surface normal reaction किस direction में apply करेगा? Perpendicular to it. So it will apply a normal reaction in this sort of direction. So that's along, you can see that's along this axis. This axis is perpendicular to this one, along this axis. Okay. So if at that point where the normal reaction is acting, you just draw a vertical axis like this, you'll see that this is forming a right angle triangle. So this angle is how much now? It's 90 minus theta. So this angle has to be theta. No? So this angle has to be theta. Okay. So the normal reaction कैसे act कर रहा है यहाँ पे? It is always acting in a direction which is making an angle of theta with a vertical. The normal reaction is acting along a direction which is making an angle of, this angle is theta with respect to the vertical. Just a minute. Seem to have lost that. Yeah. Always act along this kind of an axis. Okay. So that's the simple rule of thumb to remember. Inclined plane का angle अगर horizontal से theta है, so normal reaction का angle vertical से भी theta हो जाता है. But just remember this simple principle, this conversion. Is this clear to all of you? Okay, good. Okay, so so this is something very important to keep in mind. This very short way to understand this. If inclined plane is at theta to the horizontal, then normal reaction will become at theta to the vertical like that. Okay, now coming back here. So whenever we are applying Newton's second law or this equation, this is the equation of Newton's second law, to a situation or to a body on which multiple forces are acting, okay, we use the free body diagram method. For the vector addition, for the vector addition of forces on left hand side. In short, this is called the FBD method. So this is something very important. This is the backbone of solving all Newton's laws problems. So in FBD method or free body diagram method, what we do is, instead of showing the body like we've done in the previous example as a shape like this, if there are forces, let's say F1, F2, F3, whatever, at various angles and all that. The body in the free body diagram, in a free body diagram, the body is represented by a point mass or like a particle. So instead of showing the whole body of mass in, we just represent it by a single point mass, okay, and then show the same vectors acting on it. So first of all, the body is represented by a point mass, okay, and all forces are drawn from the point mass. They are drawn as vector arrows. And finally, vector resolution is used to show components of forces along x and y axis. Okay. And once that is shown, what happens? That Newton's second law, that net force is equal to mass into acceleration, is now solved in component form. This is solved in component form as Fx is equal to mass into x component of acceleration. Fy is mass into y component of acceleration, where Fx is sum of all x components of forces, and Fy is sum of all y components. Okay. So I'll take you through the method once more, but again, for example, we had done that question where we showed on this block there was some force acting like this, suppose. In that example we had done. ये force ऐसा act कर रहा है such that it's making an angle theta with the horizontal. So what we do is, to solve this problem, man is lying on a smooth surface. Lying on a surface like this. So to solve this problem, what we did is, what we'll do is, we will make a free body diagram. Okay, or what in short form we'll call as FBD. So in the free body diagram, we don't show anything else. We just represent the body by a point mass. So that entire mass of the body is represented by a particle. And then we show all the force vectors acting on it. So what all force vectors are acting on it? There is the external force F, which we have applied at some angle theta. So this is there. But apart from this, there is mg and normal reaction. So there are three forces acting in all on the body. There's normal reaction, there's mg, and there's this. So this is done. Then next step, what we do is we resolve the forces. So on resolving the forces, yes, it is done for so that it becomes, like a convenient way of just following some steps. So normal reaction and mg are already resolved, so we don't need to do anything. Okay, but f के components ले लेंगे. So f का यहाँ पे x component क्या हो जाएगा? F cos theta, and y component क्या हो जाएगा? F sin theta. So now my resolution is done. And now suppose the body was having an acceleration in the original diagram. Suppose the acceleration in the original diagram was E like this. So in the free body diagram, you can see that acceleration is along axis. So now this equation, that net force is equal to mass into acceleration, this is written in component form. That along the x-axis, the net x component force should be mass into x component of acceleration. Along the y-axis, the net y force, this is net, okay, not just, should be equal to mass into y component of acceleration. Now in this particular case, along the x-axis there is only one force acting, there is F cos theta. And the x component of acceleration is nothing but ma. I mean, it's nothing but a, because you can see. Okay. But along the y-axis, what is happening? The forces acting on normal reaction, F sin theta, are acting along the positive y direction, and minus mg because it's acting along the negative y direction, and this should be equal to how much? This should be equal to 0 because my y component of acceleration is 0. Okay. So this will give me equation 1, this will give me equation 2, and solving equation 1 and 2 will get the answer. So this particular method of solving is called the free body diagram method, where instead of making a diagram with a lot of detail like this, we just represent the mass by a point mass and just show the vector forces acting on it. We don't show anything else. So indirectly, we have already used free body diagram in the questions that we solved, but this is a more systematic way of representing the free body diagram method. Okay. So how do we apply the free body diagram method? Any situation where a body is acted upon by multiple forces, first of all, represent the body by a point mass. Okay. Then secondly, all the forces which are acting on it, draw them as force vectors from that point mass. Then the next step is resolve the forces using the concept of components into components along the x and y axis. And once you resolve it into components in the x and y axis, convert your vector formula, net force is mass into acceleration, into two scalar equations, the x component of force and the y component of force, like this. Okay, so have you understood this concept of free body diagram? Now this FBD concept is explained in a lot of detail in both the reference books as well as in your module. So if you particularly have Resnick Halliday as a reference book, then you can go through it, and from Resnick Halliday, that will be the best source. Otherwise, just go through it from how it is given in H.C. Verma or your module, and then just review all the questions we have done today from that perspective. And DC Pandey also gives you some idea about free body diagram. So any book which has a lot of questions solved in Newton's laws will always make use of free body diagram method. So now you have to get used to this method gradually, that any situation where forces are acting, you are able to convert it into a free body diagram and then apply the principles of vector resolution. So like this situation, I've converted into a free body diagram. And next step, what I've done is I've resolved the forces, and then I've applied Newton's second law in component form. Instead of in vector form, I've applied it in component form. Yeah, Yojit, I will send you a list of questions to be done from H.C. Verma, but more importantly, I'll send you an independent assignment also. Okay, and you can try those questions also. Cengage also, you can go through the solved examples, start going through the solved examples of free body diagram method. Okay, so people, that's it for today's lecture. So make sure you review the lecture notes very carefully today, because we have done some very important examples of normal reactions in various situations and the application of free body diagram in that. So please make sure you review those methods first and then start the assignment problems which I'll send you. Okay. Yes, I'll send today's recording and the response, both of them. Don't worry. Okay. So that's it for today, people. All the best and thanks for attending.